The Fredkin gate is a 3-qubit gate in quantum computing, also known as the controlled swap gate. It is named after its inventor Edward Fredkin. The gate swaps the second and third qubits if the first qubit is in the state ket 1, and leaves them unchanged if the first qubit is in the state ket 0. To understand the working principle of the Fredkin gate more intuitively, we can think of it as a controlled swap gate. The first qubit acts as a control qubit, and if it is in the state ket 1, the gate swaps the second and third qubits. Otherwise, the gate leaves the 2 qubits unchanged. In terms of its matrix form, the Fredkin gate can be represented by a 3x3 matrix that has the identity matrix on the first row and column, and the swap matrix on the remaining elements when the first qubit is in the state ket 1. When the first qubit is in the state ket 0, the matrix is simply an identity matrix. In a quantum circuit, the Fredkin gate is represented by a box with 3 wires coming in and out, with the first wire acting as the control qubit and the remaining 2 wires representing the target qubits. The gate can be used in various quantum algorithms, including quantum error correction and quantum information processing. The Fredkin gate is a quantum logic gate that operates on 3 qubits, 1 control qubit, and 2 target qubits. The gate swaps the states of the 2 target qubits if the control qubit is in the state ket 1. The truth table for the Fredkin gate shows all possible input states and the corresponding output states. The Fredkin gate is a reversible gate, which means that it can be used for quantum computation without losing any information. In other words, the gate can be applied to an input state, and then the output state can be inverted to recover the original input state. This property is important for quantum computing because it allows quantum algorithms to be executed without losing any information. From the truth table, it can be seen that if the control qubit is in the state ket 0, the states of the 2 target qubits remain unchanged. However, if the control qubit is in the state ket 1, the states of the 2 target qubits are swapped. The Fredkin gate is sometimes called the controlled swap gate because it performs a swap operation on the 2 target qubits when the control qubit is in the state ket 1. The Fredkin gate has important applications in quantum computing, including quantum error correction and quantum teleportation. It is also used in some quantum algorithms, such as the quantum Fourier transform and the quantum phase estimation algorithm. According to the calculation formula for the unitary transformation matrix of 3 qubits, as well as the quantum state transformation table, the matrix form of the Fredkin gate can be calculated. Additionally, below is another form of its transformation. Here, we provide a specific example calculation to illustrate the use of the Fredkin gate. Assuming that the Fredkin gate is applied to the basis states ket 110 and ket 101, we can use the matrix representation of the Fredkin gate to calculate the resulting new quantum states. According to the properties of the Fredkin gate, if the control qubit is in the state ket 1, the states of the 2 target qubits are swapped. Therefore, in this case, the third qubit will be the control qubit. Using the matrix representation of the Fredkin gate, we have, applying the Fredkin gate to the state ket 110 results in the state ket 101. Applying the Fredkin gate to the state ket 101 results in the state ket 110. This result is consistent with our expectation based on the properties of the Fredkin gate.